All right, so we get to continue looking at this derivative, and of course, I'm just thinking of that song, right? And honestly, it's so catchy. It's like f of x plus h minus f of x all over h as h goes to zero is the formula to find the derivative. And then there's like some other dialogue there, which is from Calculus the Musical. We'll have to play for it. It's awesome. But you just kind of think of that song, f of x plus h minus f of x all over h as h goes to zero is the formula to find the derivative. Now that's really kind of scary because now I'm realizing this is going to be posted on YouTube. So, all right, there you go. Well, all my right, that's great, awesome. I definitely my chances of singing in a competition are completely out the window. That's okay. I'll stick with calculus. Okay, so it says find the derivative. I really miss in-person learning. Okay, find the derivative of the following function, and I reminded you it's like a slope function. Okay, I mean, finding the derivative is a slope function. Okay, for this particular graph, like the one we just did. Now, remember up there, I estimated it what the slope was at 4, right? So, but I actually want to use the limit definition. Remember, the limit definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. It's like I dare you to just do that without singing. F of x plus h minus f of x all over h as h goes to 0. It's a formula to find the derivative. Okay, so and just like last chapter, until you take a limit, you must keep your limits there. So okay, fair warning, it's tedious. I get it. So we just have to kind of bear with it. Okay, be neat and organized. Limit as h approaches 0 of, so f of x plus h, so it's 1/2 x plus h squared, right? So really you're just inputting, instead of an x, you're inputting x plus h, okay? Minus f of x, so 1/2 x squared all over h. So I hope you realize, and maybe I'll go to the highlighter here, right? So it's like here's the little bit of a little bit more in addition to x that you put in, and then here's just x, right? So there's your 2 points, f of x plus h minus f of x all over h. Okay, so because we know it's 0 over 0, we know things are going to happen in terms of canceling. So we just have to do some algebra, and that's what makes this a little bit tedious and time consuming. So we have 1/2, and then if I expand that, that's x squared plus 2xh plus h squared minus 1/2 x squared all over h. And remember, h is that distance. H is the only thing that's going to go to 0. X is fixed in a way. So its limit as h goes to 0. Now, if we distribute this 1/2, so we get 1/2 x squared plus xh plus 1/2 h squared minus 1/2 x squared all over h. And again, here's where some nice things start to happen, because now I see that the 1/2 x squared and 1/2 x squareds cancel. Now, I want you to show your work. So I do want to look at, like, as much as possible on this first homework, every step you just do one thing. So now what's left over is xh plus 1/2 h squared all over h. And notice, I'll come over here, notice you can factor out an h, right? So the limit as h goes to 0 of h times x plus 1/2 h all over h. And the reason I want you to do this is because I want you to visually see we're canceling this h. Remember, we're removing that 0 over 0 because we're letting h go to 0. So if I can remove this h over h, I'm basically removing the 0 over 0. So now I can analyze what's really, really happening. So, So we go back to the color of blue. So now I haven't taken the limit yet. Limit as h approaches 0 of x plus 1/2 h. Now I can, right? So the limit as h approaches 0 means we only let the h component go to 0. So this part goes to 0. X is fixed, so I get x. The whole thing reduces to just an x. Now, remember that I said it was going to be a function. It's going to be in terms of x as a slope function. So we need a way to denote that. So the derivative symbol as a slope function is this. Okay, this is this little symbol. Go to highlighter here. So this symbol right here is called f prime. It's the derivative symbol. So it indicates that we have our function, but we did something to the function. We took its derivative. So it's called f prime of x. So that's how you, instead of saying f of x, we say it's f prime of x, or the derivative. Now, it's a derivative function. So that means now the input that we put in to this function here will give us slope values. It's the derivative values. So we want to know what f prime of 4 is. So f prime of 4 is equal to, well, you just call it 4. So that is the slope of the tangent line at 4. And see, the thing is the fact that it's a slope function. So now if I want to say, well, what was the derivative at 3? We could say, oh, it's equal to 3. Right? So this just happens to be an interesting slope function that the input gives you what the slope is. And I mean, think about this just for a second here. Like, think about like, well, what would the slope be at 0? Well, just from a input-output standpoint, it's 0. But take a look. Right? I mean, we have a picture of it. What is the slope of the tangent line right here at 0 at that instant? Well, it's a horizontal line. Yeah, it's 0. And then think about when you start letting x be negative, let's say like -2 right here. Guess what? The slope also is negative. So it's a pretty, I think, interesting, cool thing that this function anticipates all of the changes that are happening. And it's 0 when it's supposed to be 0. And it's positive when it's supposed to be positive. Okay, so let's look at another example, right? Let's use this function here and find the derivative using the limit definition. Then evaluate it at x equals -3. So a lot going on here. So remember, we must start with the limit definition, which says the limit as h approaches 0 of f of x plus h minus f of x all over h as h goes to 0. It's the formula to find the derivative, right? It just kind of gets in your head, and that's great, honestly, because now you remember it. Okay, so the limit as h approaches 0 of, okay, so f of x plus h. So there are two inputs here, right? So there's the x and there's the x. So there are two different spots where I need to now put x plus h. So it's 5x plus h minus x plus h squared. So that's all of your f of x plus h, right? Minus f of x, 5x minus x squared, all over h. And again, just to emphasize, go back to the highlighter. So there are two inputs, and here are our two inputs, right there and there. And I want you to see the structure, right? Like it's 5 times input minus input squared. 5 times input minus input squared. So it's the same structure. So we have some algebra to do before we can take that limit. So we need to hold our limit as h goes to 0. I can distribute this, so it's 5x plus 5h. And I'm going to distribute the negative while I square, so minus x squared minus 2xh minus h squared, and distribute minus 5x plus x squared all over h. And again, remember, we have a 0 over 0, so we're anticipating things to cancel, like 5x minus 5x minus x squared, positive x squared. And again, I want to see this step on this homework. So limit as h approaches 0, we have a 5h, and then we have minus 2xh, and then minus h squared over h. Notice that you can factor out an h and cancel. So again, I like to see that. Factor out an h, 5 minus 2x minus just 1h over h. And especially this first day of knowing this, I like to see you cancel that h, because remember, removing the 0 over 0. Okay, so then what does that give us in terms of a limit? Again, I'm the first to admit there's a lot of writing, right? And you might be saying, well, Mr. Brown, I already know all these shortcuts. Great. But you also need to know this. And for this homework assignment, you must use limit definition. And then there are shortcuts because this is so tedious. Like there's better ways to do it. So in order to appreciate that and where that comes from, we need to make sure we understand this component part first. Okay, so now I can take the limit because I'm not going to be dividing by 0. I know only the h goes to 0, and my limit value, which is just a function, is equal to 5 minus 2x. In other words, the derivative function f prime of x is equal to the function 5 minus 2x. So when it asks for the derivative, that's your answer, right? That function. And again, it's a function because at any point in time, you have a parabola, right? 5x, like what was it? 5x minus x squared. So you have some parabola that, its derivative, its slope of the tangent line is always changing. So at any instant, it's different. And so here we have a way to measure that at any instant. Here's its slope, or here's its derivative. And what instant do we want? We want the instant when x is 3. So what I can do then is now I can say, well, what's the derivative at, I'm sorry, I think I said 3, but I want -3. Yes, -3. So then I would say that's 5 minus 2 times that input of -3. That's 5 plus 6, which is equal to 11. That's a really steep slope. But if you think about it, if you have a parabola and you start going over here to -3, that slope of that tangent line is going to be pretty steep in a positive direction. Okay, so that's exciting. I like that. And again, if you think about what does a derivative measure, we talked about it. It's the slope. Oops. It's the slope of the tangent line. Oh, that was awkward. What the heck was that? That's crazy. Okay, so it's the slope of the tangent line. So when you hear derivative, we should be automatically thinking it's slope of tangent line. We should also be thinking about the instantaneous rate of change. The instantaneous, there it is, rate of change. Okay, so when you think about derivative, it's the slope of the tangent line, it's the instantaneous rate of change, right? I don't know, I think about it from a physics point of view, and maybe some of you in physics kind of can relate to this. Like if you think about like a roller coaster or something like that, or like this path here, and if you're tied to the path, let's go, I guess, purple here. So if you're tied to the path, I thought it was purple, it's black, sorry. You're always going to go around the track, right? But if you could release in an instant, like here's your momentum, but if for some reason, like there was a break in the track, right? It's kind of scary to think about, but like right there, like all of a sudden you could break off the track and follow your momentum, what would happen? Well, what would happen is you continue in this direction. Since you're no longer bound by the track, right? You're continuing in that green, that tangent line direction, and that's exactly what a derivative measures. Like what's happening at that instant, the instantaneous rate of change. Okay, now the last thing on this video that I'll put, it says, well, give 3 symbolic notations. Well, we've only covered one, so we definitely take notes on the other ones. One of them could be f prime of x, right? Or it could be like g prime of x if your function was g, or h prime of x, okay? But no, there's another notation. I guess you could also say like y prime. I guess that's another one I was thinking about. Instead of function notation, if it's y equals, you can call it y prime. But the one that I wanted to emphasize is dy dx. And I like that because dy dx, because you think about what does this stand symbolically. It's the change in y divided by the change in x, okay? And the reason, like with this d and the d from derivatives, but think about also from like the Greek letter delta y over delta x, right? Like you're doing the change of y over change of x, but you're doing it at an instant, at a moment's notice. And this notation dy dx is actually referred to Leibniz notation. And not to give too many spoilers in the Calculus the Musical, but it does look at the history of how calculus was developed. And it was sort of developed simultaneously or concurrently at the same time by not only Newton, who gets a lot of credit for what he did in terms of relating calculus to physics, but also by this German mathematician or Frederick Gottfried Leibniz, I think his name was. But anyway, that's his notation. Okay, super exciting, lots of good stuff. let me pause the video and let you kind of digest that and think about it and process it and go back and look, right? Go back and look at all the notes and those examples and see what kind of questions you might come up with.